All right.
Okay, maybe we should start. Can people on Zoom, can someone say something so I can hear them?
Hello.
Okay, good. I can hear you very well. Thanks. Okay, so so today what we'll do is we will finish off the review for the exam. So let me remind you, on the 30th, if you are in the Georgia group, you should come to this room. Okay, so this is the boy who is 323. And then if you're in the other group, the Bulldog group, your date is on the 2nd, on Friday. Okay. And if you can get here around 12:20, that would be really good, because I actually need to have you seated, and I need to check some IDs and things like that. So please arrive earlier in order for me to take care of that business before we start the exam. Okay. So we will start in today on applications. So there are two things we're going to do. We're going to do applications. And then after that, we will actually look at linear transformations. Okay. All right, so let's start in on applications. All right, so what I'll do is I will look at two types of applications. One is the economic model. And the other application is balancing chemical equations. Yeah, so what I'll do is I'll actually just look at these applications. We'll set up a linear system, and then you can do the rest at home if you'd like as practice, but I'm not going to necessarily go over the Gaussian eliminations. All right, so let's start off with this economic model. So let me draw you a table first. Okay, so this is like we've had in the past. So I have three sectors. There's the agriculture sector. There's the energy sector. And then there's the manufacturing sector. And then what's going to happen is each of these sectors is going to redistribute some of their resources. So let me just draw over here. Maybe I should just draw in a different color. So let's do it in green here. So over here, this line will sort of indicate how much like agriculture keeps and how much it gives the energy and how much it gives the manufacturing. And then I have energy here and I have manufacturing over on this side. Okay. Oh, bless you. Okay. So what happens with agriculture is it's going to keep 20% of its resources. It's going to give 40% to energy, and it's going to give 40% to manufacturing. Energy is going to keep 10%. It's going to give 10% to agriculture. It's going to be a pig and keep 80%, and it's going to give 10% to manufacturing. And the manufacturing will give like 30% to agriculture, and then it'll give another 30% energy, and then it'll give 40% to manufacturing. Okay, so we have this table, and from this table, we can sort of interpret how much each of the sectors is actually going to have. So the agriculture is going to have 2/10, it's going to keep 2/10 of what it has. And then we have 4/10 of E plus 4/10 of manufacturing. Okay. And then the energy. So what should these fractions be? How much of agriculture should it have?
1/10.
Good. And then energy will be 8/10. Right? And how much manufacturing?
1/10.
Okay. And similarly, manufacturing, it's 3/10 agriculture, 3/10 energy, and 4/10 manufacturing. Okay. So here I have a linear system, and I want to sort of balance everything out. And so, I have to put the A to the other side. So what do I get? I get a linear system where I have 8/10 of A plus 4/10 of E plus 4/10 of M is 0. Okay, so that's the first equation up here. Okay. And then the second equation is 1/10 of A plus minus 2/10 of E plus 1/10 of M is 0. And then the last one is 8/10. Oh, sorry, it's not 8. It's a 3. Let's do that. Okay, so it's 3/10 of A plus 3/10 of E plus minus 6/10 of M. 0. Okay, so this is a homogeneous system, and now I'll let you just solve. Okay, so in order to solve it, just put it in this matrix like this, and then the coefficients are 8/10, 4/10, 4/10, 1/10, minus 2/10, 1/10, and 3/10, 3/10, and minus. Okay, so you can solve using Gaussian elimination. Okay, so you should go over an economic model or two. Something from your homework would be good. And so you should know how to do problems involving economic model. Okay, so let me give you an example of balancing chemical equations. Okay. So the idea is that you take two chemical compounds with certain numbers of atoms, you put them together, there's going to be some sort of reaction, and then you get some other compounds coming out. So let me give you an example. So so C will denote carbon, and O will denote oxygen, and H will denote hydrogen, and N will denote nitrogen. Okay, so I have these various atoms. All right, so I'm going to mix two things together. So I'm going to take caffeine, which is C8H10, N4O2. Okay, so this is caffeine. Let me just do this. And I'm going to put oxygen together, O2. And what I'm going to get is carbon dioxide, CO2, plus water, of course, that's H2O. And then I get nitrogen dioxide. So this is NO2. Okay, so let me just write in these. There were one, so let me use red. Okay. All right, so this should be caffeine. Let's see here. Okay, so that part's caffeine. So this is oxygen over here. And I get carbon dioxide. That's the CO2. And this is water, H2O. And this is nitrogen dioxide. Okay. All right, so the idea is that what I want to do is I want to take certain combinations of these compounds, and I want to actually balance the number of atoms out. Okay. All right, so how do we express that? Well, I want to take X1 times C8H10 N4. I don't want to use red. Let me erase just for a second. Make it so I'm going to change this back. Okay, so let me try it. I want to take X1 times C8 H10 N4 O2. And I want to take X2 of O2, and I want this to be equal to various amounts on the right-hand side. So that's X3 CO2, X4 H2O, plus X5 NO2. Okay, does that make sense? All right, so now what we want to do is we want to just compare each of the various compounds, and from there we're going to get linear equations. So let's compare the one involving the carbons. Okay, so from the first one, how many carbon atoms do we need to take? 8 times X1. All right. Now, do we get anything from x2 at all? Yes or no?
No.
Okay, so that's going to be equal to, okay, how many carbon atoms on this side I get? X3. Okay, and any from the rest?
No.
No. Okay. All right, now we compare the hydrogen atom. So the first one I get, how many hydrogens in the first someone say it. 10, good. And none from the next one. None from X3. 2 from X4. And none from X5. Okay, we'll just keep moving down. Kind of fun doing this. Let's see. So this is going to be 4x1 for nitrogen. No, none for x2, none for x3. How many for x4? None, right?
0.
How many for x5?
1.
1. Okay, and then we only have one left, namely, well, I kind of put them in a weird order. But I should put the oxygen one down next. Okay, so oxygen. So we have 2x1, and then we have an x2. And on this side, we have 2x3, and we have an x4, and we have how many x5s?
2.
Isn't it 2x2?
It is right, 2x2, thank you. Okay, so 2, 2, 2, 4, 2, okay. Ooh, did I make a mistake? No, it's good. Okay, so does everyone see how we got these equations? All right, so now what we can do is we can sort of linearize them. So, let me just do that over in the next line. So 8x1 minus x3 is 0. 10x1 minus 2x4 is 0. 4x1 minus x5 is 0. And then lastly, 2x1 plus 2x2 minus 2x3 minus x4 minus 2x5 is 0. Okay, so we're left with a homogeneous system of equations. And what can I do? I have an 8 here, 0, minus 1, 0, 0. Okay, so that's the first equation. Okay, the second equation is what? 10, 0, 0, minus 2, 0. Okay, third equation, 4, 0, 0, 0, minus 1, 0. And then the last one is 2, 2, minus 2, minus 1, minus 2. Okay, so we're left with a homogeneous system, and then you can go home and you can solve this. Okay, so this is what how you sort of set everything up. So we solve the Gaussian elimination. Okay, so you should be able to balance chemical equations using linear algebra. Okay, any questions on this?
I have a quick question.
Sure.
So this is a different sort of, you actually wrote out the equations. Last example that you did with this chemical like balancing, you kind of made a sort of a lattice of like the chemicals going down the rows and the X's on the columns, and you skipped like the step of making the actual equations. So you just moved x1, x2, x3, negative x3, negative x4, negative x5 equals 0.
So here are the equations up here with C, H, and an O. So I'm comparing like how many, when I look at like the carbon atom, for example, how many carbon atoms I have to take on the left-hand side as opposed to how many carbon atoms I have to take on the right-hand side.
Yes, so ultimately my question would be, can we go straight to the matrix or do we have to show these intermediate, I guess,
Show your work.
okay,
Show your work. I mean, that's part of the whole exercise about doing written homework, right? Is to make sure that we show our steps on how we got the answer. Okay. So you should actually write out, you know, and I'm giving you the recipe on how to do this, right? Just, you know, write things out in terms of these equations, change it to the homogeneous system, plug it into the matrix, and then crank it out. Okay.
all right, thank you.
Okay. All right. Other questions? All right. So the last topic we need to cover is the topic of linear transformations. All right, so this is one of the definitions that you're going to be accountable for. So let me make sure that we first define a linear transformation. So definition. So T from Rn to Rm is a linear transformation if and only if T is a function such that, well, such that two things have to happen. Preserves that vector addition and scalar multiplication. So one, T of x1 plus x2 is equal to T of x1 plus T of x2. Okay, so whenever I add two vectors, T respects the vector addition. And two, T of lambda times x is equal to lambda T of x. And here x1, x2, and x are in Rn, and lambda is just a scalar. Okay, any questions on this definition? All right. So let's look at the classic example of a linear transformation. So let's say A is a m by n matrix. So whenever you have an m by n matrix, you can always create or think of A as a linear transformation. So you can let T of x be equal to just A times x. Okay. So then T is a linear transformation from Rn to Rm. Okay, so whenever you have a matrix, you can always create a linear transformation by just multiplying vector x times a. Now, we have sort of the process that goes in reverse too. So let P be a linear transformation from Rn to Rm. Okay. Then I want to actually find a matrix which represents T. So, now let E1, E2 up to En be the unit vectors in Rm. Or it's the ones where epsilon j is equal to 0, and then there's a 1 in the j spot. So this is in the j position. Okay. All right, so then t of x is equal to a times x, where I can represent a by just taking what the values of t are on the standard basis, or on these unit vectors, and put them down the columns. Okay, so I look at what the image is under t of these unit vectors, and then I just put them down the column. Okay, so maybe we should do an example. An example of an example. Okay, so suppose that t on, let's say, 0, 1 is equal to 3, 5, and t of 1, 0 is equal to 6, 1. Okay, so this is kind of written in a reverse order. But then t on x, so I put t of 1, 0 down first, right? So this is going to be 6, 1, I guess. And the other one will be 3, 5. And this is your A right. Okay, any questions on this?
Sorry, I couldn't hear you. Can you repeat like the last sentence you said?
Oh, so this example I have where t of 0, 1 goes to and t of 1, 0. And so what I want to do is I just want to write out t as a linear transformation via this matrix A. And this matrix A is just obtained by taking t of 1, 0 and putting it down the first column, and t of 0, 1 and putting it down the second
So that's not a 6, it's a 0.
column. Let's see.
To the left of 3, it kind of looks like a 6.
Yeah, so this is a 6, 1.
Oh, okay.
Okay. Yeah. Any questions on this? I think you've done problems on this. So. All right, now let's review on the idea of onto and one-to-one. So if t is a linear transformation from Rn to Rm, then t is onto if and only if the image of t, so t of Rn is all of Rn. Okay, so remember this is the image of t. So every vector in Rm gets hit by something in t. So what we can do is we can sort of reduce this down to a system of equations problem. So if t of x is equal to a times x, so we know we can do this, right? So then t is onto if and only if ax equals b has a solution for all b in Rm. Okay, so if I take any b in Rm, I look at ax equals b, I want to have a solution for this. Okay, that says that I can find an x for which t of x is equal to b. So b is in the image of t. Okay, so we actually, so if I ask you like, the proof a linear transformation is onto, you should reduce it down to this sort of matrix situation. And then you can use Gaussian elimination to check whether T is onto or not. Okay. So here you can use Gaussian elimination to check whether something has a solution. And then we showed earlier that T is 1-to-1 if and only if Tx equals 0 implies that x is equal to 0. So this is equivalent to if Ax equals 0, this implies that x equals 0. All right, so the idea is that T is 1-to-1 if and only if Ax equals 0 has only the trivial solution. Okay, so if I take a homogeneous system of equations, I want to show that you only have the trivial solution. So namely, you can't have any free variables once you do Gaussian elimination. Okay, so you can use Gaussian elimination here to also check whether T is on, is 1-to-1 or not. Okay, any questions on this?
Yeah, I have a question.
Go ahead.
So for the onto, when we're
Yes.
proving it using Gaussian elimination, when you have the matrix set up,
Yeah.
is the rightmost column, is that going to be like B1, B2, B3, etc.?
Yes.
And then you try to, you make sure that there's no values where it doesn't work?
Yes. That's
Okay.
correct. Very good.
Thanks.
Okay.
How are we allowed to like prove if something is 1-to-1 or onto based off the rank of the reduced matrix?
Well, you should just, I mean, you can, but we haven't introduced rank yet. So
Okay.
I would just do it using, Gaussian elimination. Just set it up so that in this case, you set up your matrix so that here's your A, and then here's your B over here, and then you just want to see if there's a solution for every single B. And then down here, you just put your A over here, and then you put the 0 matrix over here, and then see if you only have one solution. Okay? Okay, other questions? Okay, so I'm going to now open it up for just general question and answer for the midterm. So if you have any questions on any of the material that's been covered up through section 1.9, please feel free to ask.
Yeah, I have a question.
Okay, go ahead.
So while we were doing in one of the homework problems recently, there was one of the question asked to describe the standard matrix that would happen after a shear and then a vertical, like a reflection across the line y equals x.
Right.
So how would you go about doing that?
All right. So let's look at, first of all, okay, so can you describe the shear for me?
The actual shear said E1 stays the same while E2 turns into E1 minus 2E2.
Okay, and this linear transformation T is from R2 to R2, right?
I believe so, yes.
Okay. All right, so first of all, let's describe the shear first. Okay? So T is going to send E1 to E1. And then T is going to send E1 here to E1 minus 2E2. Okay? So
Gonna
E1
send E2, that second one should be T of E2, not E1.
Now, E1 is just 1, 0, and this is 2 times 0, 1, right? So I get 1 minus 2. Is that what you got? Yes. Okay, so then T of X is going to be equal to, well, I'm going to put 1, 0 down here, and 1 minus 2 down here, and that's X. Okay, so is that clear? What you're doing with the shear?
Yes.
Okay. All right, so now I want to do this other thing, this reflection. And let's call this thing S, and it goes from R2 to R2 also. Okay. And so what are we doing? I believe we're reflecting over this line, right? So Y equals minus X. Is that right?
I believe so.
Okay. Now, what we need to do is we need to figure out where the standard basis goes to. So if I take the vector here, 1, 0, and that's E1, where does it go to under this transformation? Well, it gets reflected and it goes to this vector over here. Goes to this vector over here, right? So this is this vector here is T of E1, and that's the vector 0, 1, minus 1. Is that okay?
Yeah.
All right. And then what you do is now you have to look at this vector up here. This is E2, and then this vector is going to go to this one over here. Okay, so this is T of E2, and that's the vector minus 1, 0. And that's an S. This is an S, not a T. Okay. All right. So, so what is S? S of X is equal to S of E1 is 0 minus 1, and this is minus 1, 0. Okay, is everything okay so far?
Yeah.
Okay. All right, so what am I going to do first? I'm going to do the shear and then the reflection. So I'm going to take a shear, and then I want to apply a reflection after that. So that's the composition of these two functions. Okay? And so, so the first thing is that's going to be S of this first matrix here, 1 minus 1, 1, 0 minus 2 on X. Okay, and then S of X, you just plug all this stuff in for X. So it's 0 minus 1 minus 1, 0 times 1, 1, 0 minus 2 times X. Okay, and then you just have to multiply the matrices to get the answer. Okay, so just multiply the two matrices and then you get the answer for the linear transformation.
Okay, thank you.
That makes sense. Okay, good.
I had another question on that. How would that change if you were reflecting across the origin? I was a bit confused on that versus like a line.
Well, I'm not sure what you mean by reflecting across the origin. That's sort of not.
Or like, I don't know, the book or textbook showed something where there was a transformation across the origin.
I think I have to look at that. It sounds a little bit, it's a little bit unclear to me what that actually means.
Okay, I guess I can email you then.
Okay, other questions?
Could you scroll down, please?
Sure.
Thank you. So for the answer that I got for this, was like one matrix. Like I didn't leave it like written out like this. I can go look for my answer, but is there a way to condense?
You just multiply these two together, right?
Okay.
So what's the answer? It's going to be 0 here, and then you're going to have a 2, I believe, and then -1 and -1.
Okay, thank you.
Just multiply that. Okay, other questions?
It seems like the textbook's definition of rotating through the origin is, or reflecting through the origin is the same thing as rotating 180 degrees.
Oh, okay. So then that's not so hard. Okay, so sorry. So you said reflecting 180 degrees.
Yeah, like reflecting through the origin is the same as rotating 180 degrees.
Yeah, so you can actually write that out, right, in terms of what it does to like 1, 0, and 0, 1. Yes, I mean, let me just, I'll just do it over here. So you're going to rotate it 180 degrees. So I guess you want to rotate it this way. And so this vector here goes to -1, 0. Yeah. And then this vector here, 0, 1. So I'm going to go 180 degrees. So this is going to go to 0, -1. Okay. So remember, you just have to know where the unit vectors go to. And that tells you everything about the linear transformation. Okay, questions? Okay. Yeah, so like I said, if you have any like questions before the test, just send me an email or something. I'll try to get back to you before that. Again, there are going to be 5 questions on the test. They may have like a couple parts to them, which will be related. And then they'll be worth 20 points each. Okay, and their partial credit will be given. So make sure you try to show your work. The more work that you actually show and indicate that it's correct, of course, the more points you get. Okay. All right. Okay, so I look forward to seeing some of you on Wednesday, and then the rest on Friday.
I have one more question about the homework. Is the stuff we did last week due next week?
Yes. So let's make sure. So section 2.2 and 2.3. Okay. So that is not due on Wednesday. It's due the following Wednesday.
Okay. Thank you.
Okay. So that's kind of the way I try to set it up so that you don't have homework due the week of the midterm.
Okay. Awesome. Thank you.
Do the week after. And I have to, of course, like make sure that the subject material is sort of the material that you kind of get back mostly from the grader.
Yep, thank you.
You're welcome. Okay, other questions? Okay, if not, we will see you on Wednesday and Friday.
Thank you.
Thank you.
Thank you. Have a good day.
You too.